5 o'clock, 5:01 actually. Now let me make sure that I'm sharing on the right screen. I'm a little concerned because I don't see the usual border. It says I'm screen sharing. Oh God, what am I screen share? What am I sharing? Well, let's bring up this chat window. What's the story? Can somebody type in the chat and say, what are you seeing? Are you seeing the right screen? The one
Yes,
that's
right now we're looking at the notes, 11.2 on tensors.
okay, good. Okay, that's ideal. All right. Thank you. So you're seeing the right thing. It's just that the border no longer lights up. Okay, before I start doing that, though, let me do another example, an example that's in fact relevant to the homework that's due next Monday. And right, here's the problem. I thought I would work through this problem for you, and then that could serve as a model for the one or two of the homework problems. So the idea is, once again, azimuthal symmetry, which often happens in physics problems. When you have azimuthal symmetry and you also have Laplace's equation, then things are rather simple. In other words, what you've got is you've got a solution like this, a PL of cosine theta, Legendre polynomial of cosine theta, and then you've got these r to the L and r to the minus L minus 1. These are things that you've probably seen in electrostatics classes. And I used them either yesterday or Tuesday to show you how to do the potential outside a charged circle. That is relevant to the homework to do Monday. Unfortunately, I did this example on Tuesday or Wednesday. Anyway, the potential inside a hollow sphere. So we want to find the electrostatic potential phi of r and theta, because we have azimuthal symmetry, inside a hollow sphere of radius r. And here we can have spherical coordinates, but with no phi dependence because of the azimuthal symmetry. And in fact, what you have is spherical symmetry. You don't just have azimuthal symmetry. So it's given by that same equation. The solution of Laplace's equation in general is like this, a sum over all L from 0 to infinity. But since we're talking about the inside of a hollow sphere, we've got that there are no charges inside. You have nothing but vacuum inside the sphere of radius capital R. And consequently, all of these terms, the BL B1 times r to the minus 1, or B0 times r to the minus 1, that is would be associated with a charge at the origin, but there's nothing inside the sphere because it's hollow, and so there's no charge at the origin, and so all the B's have to vanish. And so what we have then is just a sum over the ALs, r to the L, PL. And now we have a boundary condition, r, phi of r and theta. I took it to be v sine squared theta. Well, sine squared theta, let's see, maybe I can get the screen organized a little better. Okay, so now we've got a better screen, and I can, so let me do this. I'm, all right, here we go. So I guess I'm going to go to red. Boy, something is strange today. This pencil is not clicking the way I'd expect. Maybe it's doesn't have enough of a charge. Anyway, the point here is that P2 of x is 3x squared minus 1 over 2, if I remember correctly. And so what and of course, sine squared is obviously 1 minus cosine squared theta. And so this is sine squared is 1 minus x squared, since we're in Legendre land, where x is cosine theta. And so if we just compare this equation with this equation, sorry, those are my grandchildren. We can write sine squared theta as 2p0 minus p2 cosine theta, p0 just being 1. And then comparing this with that, we see that a0 is 2v over 3 and a2 is minus 2v over 3r squared. The 3r squared is because AL capital R squared is equal to this structure here, P2 cosine theta over capital R squared. Anyway, so what we wind up with then is this expression, 2v over 3 P0 minus R squared over big R squared, P2 of cosine theta, and then 2v over 3, 1 minus R squared over capital R squared, and then 3 cosine squared theta minus 1 over 2. I should probably put a parenthesis around this. So let me do that in live. Let me do that live. So that was the example that I wanted to show you. Now I think I'm going to skip ahead to a new chapter that I've added. As I said, the fact that general relativity is now 100 years old, and it's become more important in physics. What with the two mysteries that we have are dark energy and dark matter, and they both involve gravity, at least cosmology, well, which involves gravity. So let me first start out with general coordinate transformation. So, and here I've added a chapter called tensors. And basically, if you change from one set of coordinates, and typically we're going to be talking about x to be x0, x1, x2, x3, but of course we could be just considering space, in which case we'd have x, y, z, and this such is actually such. So to go from the ordinary coordinates, Euclidean coordinates plus time, rewritten as distance, ct, to some other set of coordinates, it's a general coordinate transformation if the x primes, x prime 0, x prime 1, x prime 2, x prime 3, are smooth one-to-one functions of the original 4 coordinates, and at least locally. Sometimes you have things are smooth and one-to-one over a certain range of certain volume or 4 volume of coordinate space, but you can't do the whole universe as one-to-one and smooth, but it depends. Sometimes you can, sometimes you can't. For the actual cosmology that we're talking about, I think basically you can. Now, because the map is one-to-one, the inverse map exists, and then that's for functions, smooth functions. We'd want it to be them to be smooth functions of x prime that give you the original coordinate. So you can go both ways. You can go here. Let me switch to black. Maybe you can go from xi's to x prime i's, or you go from the x prime i's to the xi's. And the idea is that we don't want any mathematical difficulties. So in general, we think about things as being smooth and one-to-one. So what are tensors? Tensors are simply mathematical quantities that change simply under general coordinate transformations. And let me just stress here that you probably had a course on special relativity. That's a special kind. That's not a general coordinate transformation. It's a linear transformation of a special kind that preserves the metric of flat spacetime. Here we're talking about general coordinate transformations, and that's the remarkable thing that Einstein saw, namely that one could write the equations of physics in terms of tensors, which transform simply under general coordinate transformations. The simplest tensor, of course, is a tensor that doesn't change at all, and that's called a scalar. So you change coordinates, s prime is s, and s prime of x prime is just s of x. And the temperature at every point in the room at a given time might be a scalar field. By the way, a field is a physical quantity or a mathematical quantity that is a function of the coordinates. So that's what that term field means. The next simplest tensor is a vector. And vectors come in 2 kinds, covariant and contravariant. A covariant vector is a quantity that transforms like a derivative. And in particular, the derivatives of a scalar field form a covariant vector. And this is what we call the gradient of the scalar. So this thing, v sub I of x, is the partial of the scalar field because it depends on x, with respect to xi, and this is then a covariant vector. And why is it a covariant vector? Or let us say, how does it transform? Well, it transforms very simply. V prime sub I of x prime is the partial of s prime of x prime with respect to x prime. So everything's primed here on this side. But then s prime of x prime is s of x because s is a scalar. And now the derivative with respect to x prime, well, as the chain rule tells us that the partial of s with respect to x prime I is the partial of s with respect to xk times the partial of xk with respect to x prime I. And then you sum over k from 0 to 3, or if we were in a different space, if the x's and x primes ranged over a different set of variables, 3 variables, say, or only 2, or we're in some generalized theory, a larger number of variables, then we'd have to sum over all of them. And any VI that transforms this way is said to be a covariant vector. So the derivatives define what a covariant vector is. And the coordinate differentials, dxi, define what a contravariant vector is. And in particular, the chain rule tells us that the relationship between the dx's, the dx primes and the dx's is that dx prime I, or dxi prime, is the partial of x prime I with respect to xk times dxk. And so that is our typical contravariant vector, and it then provides the rule for all contravariant vectors. Any quantity vi that transforms such that v prime I of x prime is the partial of x prime I with respect to xk times vk of x, summed, of course, over k, under a general coordinate transformation, is a contravariant vector. So I probably should have put this phrase up here that changes under a general coordinate transformation to is a contravariant vector. Okay, so we have 2 ways. The covariant ones are the ones that transform like derivatives, like gradients, and the contravariant ones are the ones that transform like dx's. Notice that I've been using here Einstein's summation convention. Whenever an index appears both upstairs and downstairs in a monomial, the index is summed over that index. Now, the reason why I said a monomial is one might have a formula, fi is vi plus bfi. Well, there the index I occurs twice, but it's not in the same monomial, so we don't invoke Einstein's summation convention. But whenever it appears instead something like this, gi or g something else, gk, say, well, hold on, I've sort of made a mess there. Okay, so suppose we say gk is equal to, oh Lord, I'm making many messes here. VK, BKI, BI. Okay, here the I occurs twice. It's the same monomial, and so you sum. So this is sum over I, BK, I, BI. But here, no sum. So that's why I say in a monomial. Another thing to note about these formulas is that the primes stay upstairs or downstairs. In other words, in this expression, this is unprimed, it's downstairs, it stays downstairs. Here, the I labels a primed quantity, and in fact, many people put the prime on the index. I haven't been doing that because I've thought that what's primed, what's different is the V, and it just happens to have various components labeled by I. In any event, you can imagine the prime is on the I here, and it's downstairs, so it stays downstairs. So in this expression here, the unprimed variable xk is upstairs, stays upstairs. Well, except here it's both. Well, here it's both upstairs and downstairs, and so this one stays upstairs. This one stays downstairs, And then the x prime I is downstairs, it's downstairs here. Or to look, a better example here is the I is primed, it's downstairs here, it's downstairs there. The K is unprimed, well, and we sum over it, so it's once again here, it's upstairs, 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 upstairs. Okay, now you may say, well, why is he saying this? This sounds sort of trivial. Well, in some of these equations, you have things, you have, suppose, all right, well, we'll see this in a moment. I think it's better for me to go to these notes now. This is straight out of the book. I'm trying to rewrite the book thing to take out the stuff that's sort of redundant and make things as clear as possible. So as I said, tensors are things that transform simply under general coordinate transformations, and the special tensors are, of course, the scalars and the vectors, but more generally, they're things that have several indexes and transform like this, for example. You can have a rank 2 covariant tensor. It would have 2 prime indices, and since they're downstairs, they stay downstairs on the right-hand side. You can have a contravariant rank 2 tensor, so the 2 primed indexes are upper, and they stay upper on the right-hand side, and then you can have a mixed tensor, one up, one down, and now they're both primed because they're indices of a primed quantity, and so the one that's upper stays upstairs, and the one that's low downstairs stays downstairs, and then the other two are K and L, and they are well, they're where they have to be, and then you know that you want this one to be upper and this one to be lower because you want this thing to be a rank 2 tensor, and as a rank 2 tensor, the thing that is the indices L and K are summed over in such a way that they form, in a sense, a scalar, in a sense. In other words, if NKL is by itself, it's rank 2, and this index and that index transform like this. Here again, we're summing over K from 0 to 3. Another way of saying that how these indices transform, a primed upper index transforms this way, a primed lower index transforms that way. So the level of a primed index does not change. So if you differentiate repeatedly a scalar field, and remember, field just means a quantity that's a function of the space-time coordinates. If you differentiate repeatedly, you get a tensor of rank 1, tensor of rank 2, tensor of rank 3. But in general, if you differentiate a tensor that's not a scalar, but a tensor of rank 1 or 2 or 3, with respect to the coordinates, you don't get a tensor. And this causes probably most of the complexity of general relativity is due to that specific fact. Let me just try to put the pencil back where it is so that it charges if it needs to. There's an exception to that. If you differentiate in an anti-symmetrized way, you get something that is a tensor. And so this is the Maxwell tensor of electrodynamics. It's di, the ith derivative of the kth component minus the kth derivative of the ith component. That's anti-symmetric in I and K, and it is a rank 2 tensor under general coordinate transformations. Now, if you have two vectors and you multiply them together, you get a rank 2 tensor. This is covariant, this is contravariant, these are mixed, and so forth. Let's see, there's something called a contraction, and we've seen these 2 or 3 times already, but it's good to look at them formally. You have a covariant vector multiplying a contravariant vector, and you set the indexes equal and sum from 0 to 3, or whatever the range of indices it is, then you get something that's a scalar. And so in other words, this thing really, in effect, it has no index, because under a general coordinate transformation, this does not change at all. In order to see that, let's just run through what actually happens to A, K, CK, one down, one up, under a general coordinate transformation. Well, this K prime is lower, so it goes down here. The K prime up here is upper, it stays up there. And then we have a partial of XL, partial XM here. And this upper one is summed over L from 0 to 3. This M is summed from 0 to 3. And on the other hand, we can see here we have partial XL, partial X prime K times the partial X prime K, partial XM. Well, that is just the partial of XL, partial XM. That's just the chain rule. But the partial of XL with respect to XM, that's just the Kronecker delta. So we wind up with ALCL, which is a scalar. So that's why when you take, if you have a monomial and you have two indexes that are the same, then Einstein's summation convention tells you that you sum from 0 to 3. But now we've learned that once you sum from 0 to 3, what happens is those indexes are no longer active. And in particular, AC is just a scalar. So in other words, suppose we have something that looks like this. A prime K L B, well, let me do C so that I stay with what we have here and make the fewest changes possible. Suppose we have this. Well, what is this? Well, we could write this in this way, and what would happen is we would have the K thing I'm sorry, let's do the L thing. It would be partial of, see, we have an XL prime, so this is going to be in the denominator, X prime L, partial X J, say. And then the rest of this would be, we could call this A, K, J, C, K. And that's all we'd have to do. We wouldn't have to have we wouldn't have to transform in this way the other indices, because these indices are inert because we're summing from 0 to 3 and they're equal. Similarly, the Maxwell tensor of electrodynamics, Fik, if you have two upper indices, two lower indices, and you sum over them from 0 to 3 on I and 0 to 3 on K, you have a scalar. The thing that I used a moment ago is that the chain rule tells us that partial x prime I, partial xk times partial xk, partial x prime L is partial x prime I with respect to the partial of differentiated with respect to x prime L. That's delta IL, which is, of course, the Kronecker delta. This Kronecker delta itself is an invariant tensor. And the reason for that is delta prime IL, well, it will have an I index upstairs, an L index downstairs, and then we'll have K and X, and we'll be summing over K and J. And then we set J equal to K, and we have this. Then by the chain rule, that's just partial of x prime I, partial x prime L, and that's the Kronecker delta. So the Kronecker delta, you see, is invariant under general coordinate transformations. It's an invariant tensor. Maxwell's homogeneous equations relate the derivatives of the field strength to each other. And in particular, there are four equations that look like this. And these are generally covariant tensor equations because of the anti-symmetry in FJK and the fact that we're summing. And well, they follow in a very cute way from this Bianchi identity. And maybe I should explain this again. I sort of explained it a little bit Tuesday or Wednesday. I'm not sure which. So let's skip this for the moment. I just want to say this is an example of a tensor equation. It's generally covariant. So if you change the coordinate system, you just add primes everywhere. The inhomogeneous, the four inhomogeneous Maxwell equations in general that are of tensor form look like this. It's the partial of square root of G Fik with respect to xk is the magnetic permeability, I guess, of the vacuum times square root of G J sub I. Now, what is square root of G? Well, G is the metric of space-time, and so that's actually it's the absolute value of the determinant of the metric of space-time. And one of the insights of Einstein was that well, in 1905, he had the insight to say that the insight of special relativity, and part of that was that eta ik dxi dxk, that this quantity here was invariant under Lorentz transformations. So that was his insight in special relativity, where eta, wow, what has happened here? First of all, oh my God. I just lost the whole set of notes. Does anybody know how to fix this? Undo? No. So, well, all right, I lucked out. Right, okay. So let me just use the eraser, which is, oh God. So I'm going to use the eraser. I'm going over here. Now you can't erase that kind of thing. All right, we're just going to have an N there that I just don't understand. Under special relativity, the insight was that there's something that's invariant under this kind of transformation. Well, in 1915, or probably a few years earlier than that, he had the new insight, which was deeper and harder to imagine because he was simply going beyond everybody. Previously, there had been Lorentz transformations, although he invented special relativity, so Lorentz transformations were not really thought about much until Einstein invented special relativity. In general relativity, there's this thing is invariant under general coordinate transformations. And how is that going to work? Well, in order for this to be invariant under general coordinate transformations, the GIK has to be a tensor of second rank. In other words, GIK is a rank 2 tensor. And G prime IK then, and now remember, let me just show you how you do this. IK, let us call this JL. So we're going to have I and K are downstairs variables and they're prime. So we're going to have partial X prime I, partial X prime K, partial XJ, partial XL. So this is the way the metric of space-time transforms, so that, in other words, it transforms as a second-rank covariant tensor, so that when multiplied by what's a second-rank contravariant tensor, namely the product of a contravariant vector dxi with a contravariant vector dxk, we get something that's intrinsically invariant under general coordinate transformations. So the idea then is that we've got this metric of space-time, and when we change coordinates, this thing ds squared is invariant in the same way that the ds squared of special relativity is invariant. I just wonder whether I should mention what these things are. Maybe I will. It's let's see if I can do this just straight. Suppose we have A, and we write it this way. So now we've written A as a covariant vector times a contravariant vector summed over the index. So the thing is invariant under general coordinate transformations. And this is called a one form. Now, there's something called an exterior derivative. And if this acts on just a function like s, then ds is partial s partial xi dxi. So it turns a scalar into a one form. This is also a one form. I think I'm going to switch then to blue. Now, what happens when a d hits a one form? Well, hold on. I've got an emergency here, so I have to answer. Hello? Thank you for calling. Yes. Right, the blower motor died this morning, and so if I run the heater, it could start a fire. So I basically have no heat or I have a fire. Yeah. I'm sorry, what did you say? Do I text? Well, yeah, sure, I can text. I'm in front of a computer now. Do you want me to text you something? Okay, well, let me write this down. I'm doing it on the computer. So it's 5:05. Okay, and oh God, I have no idea. The furnace is under the house. No, it's under the house. Okay, the house is very old. It's at least 50 years old. Well, that I don't know. Let me say this. I know the furnace is over 42 years old because I bought the house, or we bought the house 42 years ago. And we haven't done anything to the furnace. Yeah. Well, it's you mean ones that run on electricity? Yeah, well, I could do that. Yeah. 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 Right. Yeah. Yeah. All right. Thank you. Well, I'm gonna send you that right now. Okay. Right. Uh, uh, right. No need to, do it at, 7 o'clock or 8 o'clock. I mean, all right. Well, Well, it'll be okay. Oh yeah, but it's good. It's good to call anyway because my wife actually arrives by plane tomorrow, and I have to pick her up at the airport. Christ, I don't know, around 10 o'clock or something. Yes, you can. The thing is, we do have a dog. Um, sorry. Well, look, I've got this cell phone. You call me and I can arrange to be at the house. Yeah, my wife will be patient at the airport if there's a time conflict. All right. Thank you. Bye. You too. Okay, sorry for that. Okay, I'm sorry about the interruption, but as you can tell, I've got a heating emergency. The house filled up with smoke. Christ, filled up with smoke. 3 or 4 o'clock this morning, and it's taken until now to figure out what's going on. So I was going to say, what happens? This D is called an exterior derivative. And it's actually much easier to use than an ordinary derivative. Let me show you what happens. D on A is partial with respect to xj of AI, and then a wedge. I'm sorry, not a wedge yet. So let me undo that. Then it's dxj wedge dxi. So in other words, I'm using this formula for A. A is AI dxi, and the exterior derivative hits the A with a dj, and then hits the dxi with a wedge dxj. And what this wedge does is it's anti-symmetric. So this is the same thing as minus djai dxi wedge dxj. And of course, we're summing over I and j. And so what you see here is that you've created the Maxwell tensor here. For example, one part would be partial 1 of A2, and then dx1 wedge dx2, but you'd also have partial 2 of A1 dx2 wedge dx1. But these wedges are anti-symmetric. So let me write plus dot, dot, dot. So then this is d1 a2 minus d2 a1 times dx1 wedge dx2 plus other stuff. Oh my God. And what you see is that this is the Maxwell tensor Fik dx1 wedge. Oh, I'm sorry. Hold on. So this is F12 dx1 wedge dx2. And in fact, I think that gives us a factor of, no, this is right the way it is, I think. There may be a factor of 2 that I'm leaving out. So what this is saying is that the is that when the exterior derivative hits the one form, which is the electromagnetic field, it turns it into the when the exterior derivative hits the electromagnetic potential AI, which is this thing, then it turns it into the electric and magnetic fields in the form of Fij, or, in other words, F0I is the ith electric field apart from a sign, and Fjk is something like epsilon ijk bi summed over I or J or K or something. Anyway, it's the electric and magnetic fields. And then there's something cute about this D, namely that if you hit D, if you apply D twice, so we've already applied it once and we've got D, it's something like partial J AI dxj wedge dxi. When we apply it a second time, we would get partial K partial J AI wedge dxk wedge dxj wedge dxi. Okay, now what we see here is that this is symmetric in J and K, whereas this is antisymmetric in J and K. So DDA is just 0. And now we see how cute this is. DA is if A is the electromagnetic potential, which is thought to be a 4-vector in special relativity, but is a covariant vector in general relativity. If you hit it with an exterior derivative, you get the electric and magnetic fields, Fij. And if you hit it a second time with an exterior derivative, you get 0. But this is actually 4 equations, one of which is written here. You might say, what is the index that takes 4 values? Well, if you said, say, I equal to 1, J equal to 2, and K equal to 3 in this equation, the thing that you haven't used is 0. So this is the 0th equation. But then if you said I equal to 0 and JK equal to 1, 2, you've left out 3. So that's the 3 equation, and so forth. So there are 4 equations here. These are the homogeneous Maxwell equations, and the homogeneous Maxwell equations are then just DDA equals 0. So one has to admit that is very cute, and this is one of the many things that Cartan invented. He probably regarded that as the least of his achievements. This structure is more complicated, obviously. But here I'm just illustrating tensor equations. The tensor equations of general relativity are then something called RIK, which is the Ricci tensor, minus the metrical spacetime GIK times the Riemann scalar R is equal to, it's proportional to the energy momentum tensor. And so that's general relativity. And those are the Einstein equations for standard general relativity. So let's see, we have about 20 minutes left here. One of the many important things that Einstein realized and invented, and made sure that we understood is that a theory written in terms of tensors or equivalently in terms of forms has equations that are true in all coordinate systems if they're true in any coordinate system. And so that's one of the important ideas. Another insight, physical insight, and that's the thing. Einstein was a physicist, not a mathematician. In fact, he got some help from a friend of his, I think named Grossman, who was a mathematician. Anyway, in special relativity, as I said to you, this thing is invariant. And but in general, and so in flat space-time, you have this invariance. On the other hand, the thing that's generally invariant is ds squared with a g here, any coordinate differentials, and the g transforms this way because it's of second rank. Here, where this would be g prime and this g, but here for the idea of inertial frames, and the idea is that special relativity applies inside a sufficiently small laboratory falling freely in an arbitrary gravitational field. So in particular, the quadratic separation between 2 points whose coordinates look separated by dsyj is given by this expression, and the coefficients here are well, I don't know, actually, I find this rather obscure. So let's just stay with the physical interpretation, namely that if you have a small laboratory that is falling freely in a gravitational field, then inside that laboratory, special relativity applies. There are some curious paradoxes, by the way, that I chased down just out of curiosity a few months ago. Namely, what happens if in that small laboratory somebody's holding a charge? Or equivalently, if this is a freely falling laboratory, so if there's a charge in the middle of the laboratory, it's falling with the laboratory. And if you have tiny physicists in that laboratory, or, well, because when I say a small laboratory and tiny physicists, what I'm trying to say is that we're talking about gravitational fields that are essentially constant, that don't change in any significant way as you go from one side of the laboratory to the other. And that the time in which you do the experiment is also such that the gravitational field doesn't change at all during the tiny time that you do the experiment. So what happens if you have this tiny falling laboratory and in the middle of the lab is charge, Q, electric charge? What happens? Well, special relativity applies. So what happens in special relativity if you're inside a laboratory and there if you're a physicist in a falling laboratory, you would say, well, the charge is at rest. I'm not falling. It's the rest of the world that's doing something stupid. But I'm here stationary, not moving, speed zero, not turning, nothing. And there's a charge that's just floating in the middle of the lab. Well, it wouldn't radiate. On the other hand, you can imagine somebody who's far away from the tiny laboratory that's falling, and this person looks, and what does he see or she see? Well, what the observer sees is a charge that is accelerating because the laboratory is falling freely in a gravitational field. So the laboratory is being accelerated. So this person on the moon sees an accelerating charge, but an accelerating charge radiates. So from the point of view of the observer on the moon, the charge is radiating, but the physicists in the laboratory don't see it, don't see the radiated photons. The resolution of this in real detail was worked out by, I think his name is David Boulware, and he's been at the University of Washington for some time, did his PhD under Schwinger. What Boulware pointed out was that the charge does radiate, but it radiates in such a way the guys in the laboratory can't see the radiation. So that's the rather amusing resolution of the paradox. So this is a paradox that's been talked about for decades. And I think the resolution was, I don't know, 10 or 20 years ago, maybe 30 years ago. Anyway, it was David Boulware. I think his name was David, I'm not sure. Anyway, so the idea is it radiates, but the radiation can't be seen by the physicists because in the falling laboratory, because it's in a part of space-time that's space-like with respect to them, so they can't observe it. Okay, now if you have suppose you have a tensor that's covariant rank 2, and SIK is equal to SKI, then you say it's symmetric. If on the other hand it's SIK is minus SKI, you say it's anti-symmetric. And similarly, SKLM is symmetric if all permutations, if SKLM is equal to SLMK and is equal to SMKL and so forth. The metric of space-time is intrinsically symmetric because its only role in life is to get this right. In other words, it just has to give us the invariant distance between two events that are separated by dxi in the x coordinates. And if you transform to other coordinates, you then have a prime here, a prime there, a prime there, and a prime there. But G transforms in such a way that this thing is invariant. Of course, the Maxwell tensor is anti-symmetric, and oh goodness. Okay, I have to. Hello, Susan. Yes, Marathon called me.
And are they going to come?
They're going to come tomorrow morning.
Okay, then you'll be okay. I was going to say, in general, it took me a while to remember because you caught me at an appointment, but I'm not real fond of marathon. I mean, I like Tony and I sort of trust Tony, but I had a client who had a furnace where a part kept burning out all the time, kept replacing it, and it turned out that it was going to just keep burning out because there was something about the furnace or another part that was supplying power to that part. And I really was annoyed.
Yeah.
Because I think they cost the client like $1,500. And in the end, we just had to put in a whole new furnace, and all that money Marathon charged them was just down the tube. So
yeah.
You just need a blower motor, and it's cold, you need to get one. But I'm just saying, in general, I wouldn't use Marathon.
All right.
I was really PO'd, but a blower motor is a pretty simple part.
Yeah.
Did they ask you for your serial number?
Yeah, but of course it's under the house, so I don't know. So he's going to come over tomorrow morning, find the serial number and the kind of blower motor, and then try to get it.
Okay, while you're at it, you might ask him to give you the serial number.
Yeah.
because if another part goes wrong,
Yeah,
it's really nice if they come with the part.
yeah,
rather than then they charge you to get the part, then they come back.
yeah, yeah. Yeah. By the way, that Tony was very nice. Tony of Guiding Light. He was very nice.
If you ever need electrical stuff or know someone that does, I highly recommend you.
Yeah, yeah. All right. Thank you, Susan. I'm actually teaching via Zoom at this time, so I should get back to the students. Goodbye. I don't know how to get there. Okay. All right. Sorry for that, but as I said, we've got this heating emergency. So if you've got a tensor that's symmetric and you multiply it by something that's anti-symmetric, you automatically get 0. And equivalently, if you have tik epsilon ik equal to 0, that means that that the tik is symmetric. There's a theorem that's extremely useful and not all that hard to prove, and it's sort of intuitively clear. Suppose B is something that some mathematical quantity, you don't know what it is, but when you multiply B by any tensor of a given rank and kind, you get something that does behave as a tensor. The conclusion that you can draw always is that B has to be a tensor. So if A is a tensor and BA, and I'm leaving out the indices, but if you have for all tensors A, BA with the appropriate indices has the transformation properties that you expect, then B has to be a tensor of that kind. A simple example will be clearer than my voice, which I just than what I recited just spontaneously. So suppose BI AI is a scalar for all contravariant vectors AI. Then what we're saying here is that B prime I, A prime I is BJ, AJ. Then since AI is a contravariant vector, AI prime is partial, remember I is, the primed I is upstairs, so we have partial X prime I, partial XJ. The J is downstairs, so the J on A has to be upstairs. And then we have this structure here. And this is, by hypothesis, that's the hypothesis, it's equal to BJ, AJ. So then we just take this equation and rewrite it, and it's B prime, X prime I, XJ, minus BJ, AJ, and this one has an AJ, equals 0. But this holds for all vectors A, so we can promote it to an equation as opposed to an equation not involving A. And then we have this expression. And now we multiply both sides by partial xj, partial x prime k, sum over j, and that turns this into a Kronecker delta. And just wondering, what did I do there? That turns this into a Kronecker delta. I'm sorry. What we do is we take this equation, multiply by partial xj, partial x prime k. So this right-hand side came from this term. So then we have this expression, and now dividing by this factor, we get that. This here, of course, is a Kronecker delta, so this gives us B prime k. And so this equation tells us then that B prime k is partial xj, partial x prime k, bj. But that tells us that B is a covariant vector. So in other words, we start out with something and we're told, well, it's a scalar with any, when multiplied by any contravariant vector A, so it transforms this way. And then what you find out is then that B prime K is partial xj, partial x prime K, Bj, but that says that Bj has to be a covariant vector. And the quotient rule, though, is much more general. It's that if you have any anything that could be a tensor, but you don't know if it's a tensor, it just has a couple of indices, and if you multiply it by any tensor with the appropriate conjugate indices and get a scalar, or or another tensor of a certain kind. In other words, if B plays nice with other tensors, then B has to be a tensor. So that's basically the rule. The quotient rule says that any mathematical quantity that plays nice with tensors has to be itself a tensor. That's a way of stating the quotient theorem. This is a business of notation, and I could ask you guys to send me email or write in the chat what you think about this. There are these various notations to indicate derivatives. F comma theta is the same thing as partial sub theta, which is partial of F partial theta. So these two things mean this. Partial comma phi means that, okay. And the same thing for double derivatives. Comma theta theta means second theta derivative. Comma theta phi is double derivative theta phi. Comma phi phi is that, okay. Now, in special and general relativity, we typically use indices to label the coordinates, and rather than their names, theta, phi, x, y, z, we use indexes. And that makes everything a lot easier because we just know we sum from 0 to 3, whatever the index is. Or if we're in a more general theory, we sum over whatever the range of that index is. And so in general relativity, people often use common notation. F sub comma I is partial sub I of F, and that is, by definition, partial of F with respect to X upper I. And the F comma IK is the double derivative of F with respect to XK and XI. And if you have something funny like this, TIK comma sub comma JL, you get something that looks like this: partial to TIK, partial XJ, partial XL. And over here, same thing. And you might say, well, what about something like this? What is A comma I comma K? Well, this is, it's first of all partial A, partial X, partial X J, partial 2, partial XJ, partial XK. And actually, that's a comma up there, and I guess we have a comma there. But now this partial is partial of A with respect to X prime I. Whoops, I don't want this. Actually, now I've gotten confused as to what notation I'm talking about. Actually, I wrote that a little bit incorrectly, so let me fix this. This is the derivative with respect to X lower I prime. So in other words, and let's suppose we have a scalar. So this, which is also s comma I, is partial s partial xi, but s comma upper I is partial s partial x. Well, I see I've written so sloppily here, it's not clear what that is. So this is upper I, and this is lower I. And this is sometimes written as partial upper I s. So this is just a notation, and I guess well, anyway, it's a notation. So the question is, are you happy with comma notation? It has the advantage of brevity, and so the equations are, I think, easier to read. You don't have all those partial symbols everywhere, which can be distracting. Now, I said to you last time, and that the derivatives of tensors, the derivative of a scalar is a tensor, but the derivative of a vector or the derivative of a tensor of rank 2 or 3 is not a tensor. And so what one needs to do is to introduce a new kind of derivative such that the derivative of a vector is a tensor. And those derivatives are called covariant derivatives. And these are written sometimes like this, di vk, say, and that then is a covariant derivative. But another way of writing that is vk semicolon I. So the comma notation gets promoted to semicolon notation when you introduce covariant derivatives. And covariant derivatives are quite important. In particle physics, one typically writes the covariant derivatives this way, but in general relativity, one can use both. I've been sort of thinking of following Carroll, who doesn't much like the comma notation and the semicolon notation, but just this afternoon I picked up Dirac's book, and Dirac uses the comma notation and the semicolon notation, and my respect for Dirac is unlimited, and so I'm going to stick with the commas and the semicolons, at least for the time being, because Dirac is he's one of the great physicists, on the level of, whether he's exactly on the same level as Einstein or not, I don't know, but he's way up there among the handful of truly great physicists of modern times. So his choice means a lot, I think. All right, well, I've gone over about 5 minutes to make up for the phone calls having to do with the heating system. I'm hoping that I won't freeze to death tonight. Let me tell you, we have a colloquium tomorrow at 3:30, which will be zoomed to us from Clarendon Laboratory at Oxford University, or actually, since 3:30 in Albuquerque is 10:30 p.m. in London or in Oxford, the speaker probably will be broadcasting from home. And she's going to be talking about life from a physical point of view. And life is something that is some physicists who have thought seriously about life as opposed to me, who just am alive temporarily. The physicists who think deeply about life think of life as active matter. So it's matter that is active in the sense that in the sense that it's not in equilibrium. And of course, that's what all living things do, is they draw energy from the sun or from food and use that energy to do things. If when they die, on the other hand, they eventually become inactive matter, which is matter in which has come to equilibrium. And so living things somehow manage to avoid equilibrium for, in the case of insects, it might be months or years. In the case of people, it's 70 or 80 or whatever. All right, well, I'm dragging on, but I urge you all to tune in then. It's going to be Zoomed. I will send everybody the Zoom link and the password. The password, let me just write it down for you. The password is PANDA, and that's the password for UNM colloquia. I forget what the Zoom number is, but it's not the class password, because I'm not going to be the I'm the person who's the host, but the department wants to run the thing from the departmental computer. And I presume that if you don't want to use your own computer and get it Zoomed, you can go to room 1140, and you can probably get some coffee and some sort of junk food. All right, I'm going on and on and on, which is a little absurd. So I'm going to let you all go now, and wish you all a happy weekend. And again, urge you to tune in to the colloquium on Friday. One of the things that's an important part of your education is the colloquia. Now, not every colloquium is worth watching. And so if you're at a colloquium and you don't like it, leave the room, or turn off Zoom. But you should always tune into the colloquium or go to the colloquium and give the speaker 5 or 10 minutes before turning off Zoom or leaving the room. You might think that you're trapped, you have to stay in the room if you enter the room. I don't think so. I think that if this colloquium is inappropriate for you, you have every right to leave. So that's my view. All right, goodbye, everybody. Have a nice weekend.